Hello and welcome back to the good stuff we have been doing. Today in this video we're going to look at the integral from 1 to infinity of 1 over the floor of x squared times the ceiling of x squared, and this is from the 2026 MIT Integration B exam. Now, first of all, the key to solving this problem is to understand the roles that these functions here play. This is the floor of x. The floor of x basically is an integer function. An integer function means that it can take any numbers input, but the output must be an integer. So for example, if you plug in 3.2, so the floor of 3.2 is basically 3, because we're looking for the largest number that is less than or equal to 3.2. So numbers less than or equal, the largest integer less than or equal to 3.2 is basically can be 0, can be 1, can be 2, can be 3 also, because they are all less than or equal to, but what is the greatest of them? That is 3. Likewise, the floor of 5.2 is going to be 5. Just take the integer part whenever you get floor. So you're looking for the integer part. But on the other hand, the ceiling of x is defined to be the smallest integer that is bigger than or equal to x. So basically the ceiling of, let's say the ceiling of 3.2 would be 4, because 4 is the smallest integer that is bigger than 3.2. So this one usually is called the greatest integer functions. This one is usually called the least integer function. That is how they are defined. So since they are integer functions, it means that they only output integer value. So we need to split this interval of integration. At least we know that if you are going from 1 to infinity, you are going to pass 1, you're going to get to 2, get to 3, and then up until infinity. So basically this integral here can be equal to, first of all, the integral from 1 to 2, okay, of 1 over the floor of x all squared times the ceiling of x squared dx, plus the integral from 2 to 3 of what? 1 over the floor of x squared times the ceiling of x all squared dx, plus the integral from 3 to 4 of 1 over the floor of x all squared times the ceiling of x all squared. And we can obviously do this forever. We can continue and we get to the integral from n to n plus 1 of 1 over the floor of x squared times the ceiling of x squared, and obviously this goes on to infinity. Okay, now but in each of this interval, what does this integral equal to? Well, in the first interval, what's the floor of x? Between 1 and 2, the least integer is 1, so we are going to do the integral from 1 to 2 of 1 over the floor of x actually equals 1 here, while the ceiling of x equals 2 here. On this other hand here, this is dx, of course. From integral from 2 to 3, this equals 1 over 2 squared times 3 squared, because it is clear that on this interval the floor of x is 2 and the ceiling of x is 3, and we can continue forever obviously, and we can have that this is the integral from 3 to 4 is 1 over 3 squared times 4 squared, and so on. So if we look at this now, notice that in this integral, this is basically the sum as n runs from 1 to infinity of 1 over n squared times n plus 1 squared times the integral of n to the integral the limit of integration is from n to n plus 1 dx. Okay, so because these are constants, so we can push them out of the integral sign. So if you evaluate this integral, you obviously get 1. So it remains for us to evaluate the sum as n runs from 1 to infinity of 1 over n squared times n plus 1 squared. Now, to evaluate this sum, we recognize that this is a square. So this is a square of the sum as n runs from 1 to infinity of 1 over n, then you have an n plus 1 all squared, and you can write this as the sum as n runs from 1 to infinity of 1 over n minus 1 over n plus 1, and we're taking the square. Okay, so if you do this, you are going to get the sum as n runs from 1 to infinity of 1 over n squared minus twice the sum as n runs from 1 to infinity of 1 over n and then n plus 1 plus the sum as n runs from 1 to infinity of 1 over n plus 1 all squared. Okay, so the first one is zeta of 2 and is equals to pi squared over 6. And the second one is minus twice of the sum as n runs from 1 to infinity. We could write this as a telescoping series 1 over n minus 1 over n plus 1 too. And the third one is also zeta of 2, but I think we start at so we could write this as the sum as n runs from 1 to infinity of 1 over n squared minus 1. Yes, we could start write it this way. Yes, we could write it that way because we start from 1 over 2 squared, so we can subtract 1. Then you would have pi squared over 6 minus, here notice that this is twice of 1 because this is a telescoping series. If you plug in n equals it, everything cancel out remaining 1, so this everything here is 1. For this part you have pi squared over 6 minus 1. So this way, so you have 2 pi squared over 6 minus 3, which is pi squared over 3 minus 3. So that is the value of this problem. The integral equals pi squared over 3 minus 3. So that is equal to pi squared over 3 minus 3. So thank you very much for watching, and please do subscribe to the channel. Bye. Have a nice day.